Welcome back to the Deep Dive, where we extract the fundamental truths from deep research papers and deliver them directly to your cognitive stack. Today, we are wading into what has become arguably the most expensive debate in modern machine learning. We're talking about pre-training optimization for large language models.
It's a debate with just massive resource implications. I mean, pre-training consumes the lion's share of computation. When you look at models like, say, DeepSeek v3, the source material notes that pre-training accounted for over 95% of the total project cost.
Right, and for years, AdamW has just been the default optimizer.
It has. But recently, we've seen this flurry of new algorithms, Muon, Sophia, Soap, all of them, claiming these really impressive speedups.
We're talking anywhere from 1.4x to a massive 2x efficiency gain.
Exactly.
So if those claims were, consistently true, you'd think we'd see every LLM shop migrating immediately.
Of course.
A 2x speed up on a project that costs hundreds of millions of dollars is, it's transformative. But that widespread adoption, it hasn't happened.
It really hasn't.
So what's the disconnect? Why is there this industry-wide skepticism, despite all these sensational claims?
Well, the paper we're diving into today argues that the skepticism is it's completely warranted. And it's because the previous evaluations had two critical methodological flaws.
Okay, what were they?
First, there was an unequal or just insufficient hyperparameter tuning, which means many new optimizers looked fantastic only because the AdamW baseline they were compared against was, frankly, artificially weak.
So a weak baseline. And the second flaw?
The second was that the evaluations were often conducted on really limited small-scale models or, low data regimes that just don't reflect the high data, large-scale training environment of a modern LLM.
So the mission here was clear. Conduct a systematic head-to-head comparison to settle this once and for all.
Precisely. And this study, it compared 11 different optimizers across 4 different Llama 2 model scales. We're talking from 0.1 billion up to 1.2 billion parameters.
And crucially, they tested these across varied data regimes, going from 1x, the Chinchilla optimal, all the way up to 8x.
That's right. And the high-level conclusion, sort of the bombshell that drives the rest of this whole discussion, is that when you subject these optimizers to a truly rigorous and fair comparison,
meaning you tune AdamW just as hard as everything else?
Exactly. When you do that, those sensational speed-up claims, largely, well, they dissolve. The majority of reported 2x gains were, in reality, just artifacts of an undertuned AdamW baseline.
So the greatest optimization gain available wasn't some novel algorithm, but simply a massive improvement in configuration management and meticulous tuning of the existing standard.
That's it.
That is a profound finding, especially for the expert listener out there who is actually designing these training pipelines.
It absolutely is. And let's look at the methodology they used to prove this, because it really underscores the necessity of rigorous benchmarking. To solve that hyperparameter tuning problem, the researchers implemented a 3-phase coordinate descent framework to tune the n hyperparameters.
Okay, so for those who might not be familiar with that level of tuning, can you just briefly explain the complexity here? We're not just running a simple grid search.
Exactly. This isn't a basic sweep. We're talking about optimizing multiple interacting parameters, things like learning rate, weight decay, all the various momentum betas, and doing it until convergence across 6 different model and data settings.
And coordinate descent means what exactly?
It means they systematically optimize one hyperparameter at a time, holding the others fixed, and then they iterate that process across all n parameters until they find a stable optimum. It's an incredibly labor-intensive process, but it's really the only way to ensure they found the true ceiling of performance for each optimizer.
And what did all that meticulous tuning reveal about the status quo?
Well, the finding related to the weak baseline problem it's just astonishing. The researchers took a widely adopted standard for LLM training, a common GPT-3 recipe, for a 100 million parameter model.
Okay.
They didn't change the optimizer. They simply tuned only the learning rate for AdamW within that fixed setup.
Just the learning rate.
Just that. And that single tweak to the most basic hyperparameter yielded a 2x speedup for AdamW itself compared to the weakly tuned recipe they started with.
So hold on. Before anyone even started running these new algorithms, there was a 2x efficiency gain just sitting there, available in the standard setup, waiting to be found by proper tuning.
Yes.
That just throws cold water on nearly every historical comparison.
It proves that if your AdamW baseline is only performing at, say, 50% of its potential, then any new optimizer that hits 100% of that baseline's true potential can very easily claim a 2x speedup, even if it's no better than a well-tuned AdamW.
This also brings up the issue of hyperparameter transferability, which I know is often a shortcut people take in initial comparisons.
It's a huge shortcut. And yes, the study confirmed that optimal hyperparameters are highly specific and non-transferable between optimizers. For example, they found that Liang's optimal weight decay was around 0.6,
0.6.
which is dramatically higher than AdamW's optimum, which hovers around zero point 0.1. So if you just fix the weight decay across both, you are fundamentally crippling the new optimizer, or you're over-tuning the baseline. Treating these values as constants is a recipe for an unfair comparison.
And finally, within this benchmarking section, there's the time dimension. You can't trust early loss curves, can you?
You can't. The study makes a very strong case that intermediate checkpoints are highly misleading. If you stop trading too early and look at the last curve, your optimizer rankings might be completely wrong.
The rankings can actually flip.
They observe that rankings can flip multiple times during training, particularly when the learning rate decay schedule kicks in. So the evaluation must be done at the targeted training budget when the full convergence behavior has been realized.
Okay, let's transition now to the core scaling results, which use this rigorous methodology we just discussed. They tested this up to 1.2 billion parameters, Llama 2 architecture, high-quality data. What was the absolute ceiling they observed for speedup against the properly tuned AdamW?
Against the well-tuned AdamW baseline, the highest observed speedup for any alternative optimizer was capped at 1.4x.
1.4x. So we've gone from these theoretical 2x gains down to a 1.4x ceiling under real-world, rigorously controlled conditions.
That's the real number. And the metric is defined by the equivalent data budget needed for AdamW to achieve the same final validation loss.
Now, a 1.4x gain is still significant when you're dealing with millions of dollars, but the next finding, that's the real warning sign for large-scale production deployment. The speedup decays with model size.
It decays dramatically. For smaller models like the 0.1 billion parameter scale, you had optimizers like Muon and Soap showing an initial speedup of about 1.3x.
Okay, 1.3x, still pretty good.
But when they scaled up to the 1.2 billion parameter models, especially in that high data 8x Chinchilla regime, that speedup advantage just decayed to a mere 1.1x.
Wow. That is critical. I mean, if your gain shrinks from 30% to 10%, just moving from a toy model to a small industrial model, what happens when we go to frontier scales?
Well, the fitted scaling law, based on these results, it offers a pretty sobering prediction.
Which is?
It suggests that if you were to deploy Muon on, say, a 7 billion parameter model in the standard 1x Chinchilla data setting, you might actually end up with a higher final validation loss than if you had just used a properly tuned AdamW.
So it could actually be counterproductive.
The computational overhead and the decaying efficacy of the algorithm could make it worse at true scale.
That immediately shifts the operational calculus. It means the cost of migrating your entire training pipeline away from AdamW to adopt some new optimizer might completely outweigh the marginal benefit, especially if that benefit just disappears when you scale up.
Exactly. Which brings us to the structural insights the study provided. They categorized the successful optimizers into two main classes based on how they process gradient updates: scalar-based versus matrix-based.
Let's start with scalar-based. These are the ones we're most familiar with, where updates are done element-wise.
Yes, so scalar-based optimizers, which include AdamW, Liang, and Mars, update each parameter individually using scalar operations. After that stringent tuning process we talked about, the maximum speedup achieved by any of these methods over AdamW was less than 1.2x.
So they're competitive, but they don't fundamentally change the efficiency curve.
Not really. But the matrix-based methods, Muon, Soap, and Cron, that's where those 1.3x gains were concentrated, at least at the smaller scale.
Right. So why does leveraging that matrix structure give them an edge?
This is where they utilize more structural information. Matrix-based optimizers strategically precondition the gradients by leveraging the matrix structure in the weight tensors of the network. Muon, for instance, uses the Newton-Schultz operation to estimate the inverse Hessian, which lets it take more curvature-aware steps.
So the structural computation lets them navigate the loss landscape more efficiently. But that efficiency comes with an increased computational overhead, which seems to be what hits them hard as the model size increases.
Precisely. The key finding was that for models under 520 million parameters, these matrix-based methods consistently outperform their scalar counterparts, achieving that approximate 1.3x speedup. The gain is real, but it seems to be limited by scale.
What's fascinating, though, is the nuance about the data regime. The best optimizer seems to depend on how much data you throw at the model relative to its size.
That's the critical subtlety. Muon was the undisputed champion in the smaller data regimes, specifically 1x through 4x Chinchilla. It's highly effective when training is primarily data limited.
But then there was a shift.
Yes. The study found that when the data-to-model ratio was pushed higher to 8x or even 16x Chinchilla on the 300 million parameter models, Soap and Cron started to outperform Muon.
So why the flip? Why do different optimizers excel in these overtrained or data-dense settings?
The paper suggests it's likely due to the nature of the momentum they maintain. Soap and Cron maintain a form of second-order momentum, which appears to become more effective in these long-run overtrained settings.
I see.
So when you're deep into the training phase with tons of data, this sustained adaptivity seems to be more beneficial than the initial aggressive preconditioning that Muon provides.
And just briefly, what about the efficiency variance within that scalar family? Things like variance reduction or memory-efficient methods.
The variance reduction techniques like AdamW and Mars all provided a small but a clear measurable lift over vanilla AdamW.
And the memory-efficient ones.
The memory-efficient variants of Adam Mini and Liang, they closely tracked AdamW's performance. The cost of reducing that auxiliary state was minimal, at most a 5% slowdown, and sometimes they even showed slight improvements.
To wrap up, let's look at the generalization behavior, which was remarkably consistent across all 11 optimizers tested.
Yes, this was a striking finding. The evaluation losses and the training losses followed roughly the same trend across every single optimizer.
So what does that imply?
It implies that while the optimizer choice affects the speed at which you traverse the lost landscape, it does not significantly alter the fundamental generalization properties or the final structural outcome of the model, at least not in these regimes.
So as I said before, the optimizer is a speed dial for the descent, not a map editor for the landscape.
That's a great analogy. And finally, the study confirms some shared optimization phenomena that were previously attributed only to AdamW. They showed that parameter norms generally track the learning rate decay schedule. They increase and then they decrease.
While the gradient norms do the opposite.
Exactly. Gradient norms were consistently observed to increase during the learning rate decay phase. This is crucial because it confirms that these are general characteristics of deep learning optimization itself, not specific artifacts of the AdamW algorithm.
This systematic approach gives us serious, actionable takeaways. Let's summarize the operational intelligence for our expert listeners.
First and foremost, the necessity of rigorous hyperparameter tuning is paramount. Your biggest and safest efficiency gain is probably just tuning your current AdamW baseline.
Which eliminates the need for complex migrations and invalidates most of the sensational claims you might read.
Right. Second, matrix-based optimizers are structurally superior, but that advantage is modest to max of 1.4x, and it severely decays with model scale, dropping to only 1.1x at 1.2 billion parameters. So if you're operating a 7B model today, the evidence suggests your time is better spent on config management than on deploying Muon.
And third,
Always evaluate the target training budget. Relying on early-stage checkpoints or intermediate loss curves will give you unreliable and potentially disastrous rankings.
So given all this robust evidence that current advanced optimizers lose their efficacy as we scale past 1 billion parameters, and considering that scaling law prediction that some might actually perform worse than AdamW at frontier scales, we are left with a fundamental open problem.
The study's limitation is clear. They capped out at 1.2 billion parameters. The crucial question that remains for the industry is this: what kind of architectural or algorithmic innovations are needed to design an optimizer whose efficiency gains are stable?
Stable meaning they don't diminish as LLMs move past 7 billion, 70 billion, and toward these trillion parameter scales.
Exactly. That is the next frontier of optimization research.
Stability and efficiency at scale, the search continues. We'll be tracking that research closely. That's it for this deep dive.